Welcome to the Binghamton University Rover Team's System Acceptance Review. We are excited to show our progress and innovation this year and are proud to present our 2020 Rover, Progression. Our rover's name came from a kit submission through our Engineers Week Rover naming contest. Our team consists of 25 engineers subdivided into 4 different subteams: mechanical, electrical, software, and physical task and analysis, also known as PTA.
For our drive, we use a 6-wheel triple rocker suspension that creates a firm, balanced base for extremely tough terrain. We use the powerful and inexpensive embedded motors found in hoverboards to ascend steep slopes, climb over obstacles, and move quickly on flat ground. Hoverboard wheels alone would not be sufficient to traverse uneven terrain, so the tires were extended with custom machined spokes and Sandtrax tires. These airless tires act as shock absorbers for the rover, allowing it to safely travel over rocky surfaces. Large tires, along with a center of gravity below the frame, provides a stable base that is difficult to topple. For the chassis, we settled on a design that provides a highly customizable frame with ease of repair in mind. The chassis is made of aluminum extrusions bolted together with custom manufactured brackets. All readily available materials make these parts easy to manufacture and replace. The electronics are protected by a lightweight acrylic enclosure to protect them from the elements, and to easily spot any issues in wiring without taking it apart.
Our arm has 6 degrees of freedom and was based around the design of an excavator arm due to their robustness and capability to lift and carry loads of different mass. Its limbs are made of lightweight anodized aluminum with an extra chem film coating that we had machined by Protocase. The extra coating protects the arm from harsh environments and extends its lifespan. The arm moves using the extension and retraction of a pair of linear actuators, one controlling each limb. The rotation of the arm is handled by a stepper motor placed 90 degrees under the chassis that turns a bevel gear. A gear on the arm base catches on the motor gear to spin the entire arm. The gripper uses 3 stepper motors to precisely move with 3 degrees of freedom. The motor controlling the fingers has a gear that hits a rack and pinion on each finger to clamp down on objects. They have a rubberized coating to stick to objects. There is also a flexing element to the fingers to allow for further tightening on objects. The wrist motor can adjust the angle of the gripper and align the axes of the hex key with the axes of the gripper rotation motor, which allows it to spin.
The auger will collect dirt and dispense soil samples into the 2 testing beakers on the testing array. Our sensors are then lowered into the beakers, which are maneuvered via the rack and pinion system. As they move, the dirt sample in front will have its temperature and moisture measured, while the lagging beaker is checked for methane emissions, which would indicate extant life. The beakers are then sealed with a stopper and are treated with water and hydrogen peroxide respectively. As the reaction between dirt and the hydrogen peroxide takes place, releasing CO2 and creating free hydrogen ions, the CO2 sensor by the pump will detect any CO2 emissions, indicating extant life.
If there were no CO2 emissions, but a high concentration of H+ ions in the water mixture, this indicates extinct life. Finally, both beakers will individually have their pH taken by a pH sensor at the end of the array.
We developed a custom end-to-end software system in order to maximize reliability and performance. A custom command interface readily provides the rover operator with responsive controls and relevant information about current rover status. A custom network protocol allows for ultra-low latency communication between base station and rover endpoints. Our onboard system was built to be robust. All rover subsystems are continually monitored for failure, and connection is automatically reestablished if lost. In addition, the drive and arm subsystems utilize safety timeouts to protect the rover and its environment. Our onboard subsystems communicate using I2C, which ensures consistent message timing. In order to ease the development of autonomy path planning algorithms, a simulator was created. The ability to simulate sensor input and monitor algorithm behavior in a contained, feedback-rich environment enables a rapid write test debug cycle. Our autonomous navigation system utilizes an occupancy grid and vector field-based approach. Although waypoints can be pre-programmed by the operator, the rover is able to detect and avoid obstacles using an onboard LiDAR sensor. In addition, an accurate GPS module provides location and heading information. Finally, an open-source augmented reality library is used to detect markers and determine their distance and offset from the rover.
Our goals this year were to create a rover that is modular and robust, allowing for easier changeouts between competition missions, and the ability to construct each system individually, allowing for a faster build process. With the rover being more robust than last year, we will be better prepared for the terrain at the Mars Desert Research Station and competition tasks. Since the rover is modular, we were able to test all systems individually before placing them on the rover. On behalf of the Binghamton University Rover Team, we are very excited to compete in the 2020 University Rover Challenge. We're proud of how far we've come this year, and we hope to see you in Utah. The Binghamton University Rover Team thanks our sponsors for making all this possible.